Okay, so this time I'm going to talk about probably the most famous theorem from projective geometry and the oldest theorem of projective geometry, which is called Pappus's theorem. So Pappus lived in Alexandria, thinking about 400 AD, and he was familiar with the work of Euclid, and he established this fascinating result, which is, in my opinion, like really up there with some of the most beautiful theorems. It's very easy to state, not particularly obvious to see how it's proved, and extremely applicable to lots of situations. So what this result says is if we have distinct points A, B, C, A dash, B dash, C dash, and A, B and C are collinear, and A dash, B dash, C dash are collinear, then if we form the sort of cross joins between these different pairs of points, we'll end up making three new points, and they'll lie in a straight line. So, in particular, Pappus's theorem states that if we get the point obtained by intersecting the line from A to B dash and the line from B to A dash, and we also get the point similarly from intersecting the line A to C dash with the line C to A dash, that gives us a second point. And also we get the third point, the third sort of cross join, which is obtained by drawing a line through B and C dash and C and B dash and seeing where those two join. That'll give us three extra points, and Pappus's theorem claims that those 3 points will be collinear. This is the claim. So I find it truly remarkable. It doesn't make any reference to the positions, particularly of A, B and C, or A dash, B dash and C dash, and obviously it's a result of projective geometry, so it's extremely general. It's Pappus, I suppose, was really the sort of father of projective geometry. I think this is, at least to my knowledge, the earliest result which really naturally lives in projective geometry more than Euclidean geometry. But Pappus obviously didn't have the knowledge we have today, so he had to try and prove this result using Euclidean methods. And this is kind of awkward because there are cases where this result looks very strange in the Euclidean plane. For example, what happens when two of these lines, which are supposed to make a cross join point, never meet because they're parallel? Well, we don't have that problem in the projective plane, but we do in the Euclidean plane. Anyway, so Pappus had a rather laborious proof of this theorem, but using the results we had last time, in particular the fundamental theorem of projective geometry and the idea of the axis of projection, we can see that Pappus's theorem follows almost immediately. So, in particular, recall last time that if we have a projection and we know how that projection maps the distinct collinear points A, B and C to the distinct collinear points A dash, B dash and C dash, then that essentially fixes how this projection, or projectivity, it's the same thing, how it operates on every single other point. So, in other words, a projection is really specified by saying, by describing three collinear points and their collinear images. Now, more than that, we saw that there were some corollaries to this fundamental theorem, and one very important one was that any such projection can be written as the composition. So any such projection from a distinct line with points A, B and C on it to a distinct line with points A dash, B dash and C dash on it, any such projection can be written as the composition of two projectivities. So in particular, we do a projectivity from this line ABC to this kind of intermediate line, and then we do another perspectivity which sends the points in the intermediate line onto their final destinations at A dash, B dash and C dash. And moreover, we described how this intermediary line is actually also uniquely defined. It's known as the axis of projectivity. So it's a unique line which is associated with this projection that sends these 3 points to these 3 points, and also it has the property that if we take any 2 points, let's say A and B, and their images A dash and B dash, and we get the cross join, which is A, B dash meet B, A dash, well, that cross join point will always lie upon this axis of projectivity. The axis of projectivity contains all of these cross join points. And so now we really see that Pappus's theorem follows immediately, because we have these two lines, one with A, B and C, the other one with A dash, B dash and C dash, and we can create a projection as a composition of two projectivities, as we've been describing in the previous lecture, and that is necessarily associated with this axis of projectivity, which is precisely Pappus's line. It's precisely the line that goes through these 3 cross-join points. So we really get the result immediately. So it's interesting to note, in a kind of similar way to how Desargues' theorem was associated with this so-called Desargues configuration, which is actually the picture on the cover of Coxeter's book, which I'm mostly following. Well, in a similar way, Pappus's theorem kind of has this underlying Pappus's configuration, as shown here. And so what this is 9 points and 9 lines, and every point has 3 lines through it, and every line has 3 points on it. And so this is a self-dual configuration.